Hi, I am Melanie Sklar. I'm a third-year PhD student working with Yejin Choi and Julia Cvetkop in natural language processing.
My name is Kyle Johnson. I'm a PhD student in computer science and engineering at the Allen School, and my advisor is Vikram Iyer.
I'm Jiafei Duan, a first-year PhD student at the Allen School. I'm part of the Robotics State Estimation Lab and Ranjay Krishnan's lab.
This is a great moment to be doing NLP research. Things are changing very rapidly. I focus specifically on reasoning of large language models. One type of reasoning that current large language models don't do very well is theory of mind reasonings. A short story that people usually use to test theory of mind capabilities is called the Salient test.
Melanie works at her desk with her laptop and the attached monitor. Her laptop displays an icon of a man, an icon of a woman with a red apple overlaid, a basket icon and a blue box, as well as a timer. The monitor displays the same icons in the text Salient test, Wimmer, and Perner, 1963. Baron Cohen et al., 1985.
Say Alice and Bob are in a room where there is a basket and a box.
Melanie stands before the whiteboard and holds the red marker. She draws a stick figure which she labels Bob, and next to it a stick figure which she labels Alice. She draws a basket under Bob, and a box under Alice.
Alice has an apple here. She puts it in the basket and then leaves the room. Now Bob will come and moves the apple from the basket to the box.
She draws an apple next to Alice. She erases the apple, redraws it in the basket and then erases Alice. She erases the apple from the basket and redraws it in the box.
So the questions that then will ask either a person or a model to probe their understanding of theory of mind reasoning is as follows. Where does Alice think that the apple is? Where does Bob think that Alice will be searching for the apple when she comes back? Where does Bob think the apple is? And those questions do not all have the same answer, but language models will always answer box. The reasoning that's missing is understanding that what you may know might not match what I know.
Text on the monitor in Melanie's office reads, Salient test, Wimmer and Perner, 1983, Baron Cohen et al., 1985, Anne and Bob are in a room where there is a basket and a box. Anne puts an apple in the basket and then leaves the room. Bob then moves the apple to the box. 1. Where will Bob search for the apple? Answer, box. 2. Where does Bob think that Anne will search for the apple when she comes back? Answer, basket. An arrow which points to question 1 features text, first order, true belief question. An arrow which points to question 2 features text, second order, false belief question.
So we'll have several graphs.
Melanie sits in front of the monitor which now displays the text, graphical global state tracking. The monitor also displays the prompt and question 2 on the left side of the screen. On the right side of the screen, the word apple appears in a box with a line labeled with the text, is in. The line leads to the word box. A line labeled, is in, coming out of the word box leads to the word room. The words basket and Bob also appear with lines labeled, is in, which lead to the word room. A box with the word and stands apart. Underneath the chart the text, global context, G, is written in red.
Example 1 graph that says where will Bob search for the apple? So the beliefs that Bob have. Another graph for the belief that Bob has about Anne's beliefs. So this is what you feed to the language model, and we find that by doing this procedure you can improve the performance on a theory of mind dataset.
The monitor now displays a screen titled, Symbolic Tom's Overview. A text box on the left reads, where does Anne think that Bob will search for the apple? 2 arrows come out of the box. The upper arrow points to the text, where is the apple? Which points to a robot icon with a speech bubble which comes out of it and contains the text, basket. The lower arrow points to a box which contains a chart. The chart features the word apple with a line which comes out of it labeled with the text, is in. The line leads to the word box. A line labeled, is in, comes out of the word box and leads to the word room. The words basket and Bob also appear with lines labeled, is in, which leads to the word room. A box with the word and stands apart. An arrow which comes out of the chart points to the text, Bob is in a room, where there is a basket and a box, the apple is in the basket. An arrow which comes away from the text points to the robot icon. Text on the bottom of the display reads, 1. Detect entities in question, Retrieve belief graph and perform. 2. Retrieve sentences captured by the graph. 3. Feed to language model.
What drew me into robotics was just how interesting it is to be able to make something that can move on its own.
Kyle sits down in front of a microscope and operates on a tiny component. Uses two corded prongs to work on a circuit board in a petri dish.
And the idea with the microflyer was to take advantage of these small electronics that we've been able to fabricate in the lab in order to control how it dispersed on the way down. So our origami microflyers here were actually inspired by leaves like maple leaves that have similar falling behavior.
He walks over to a display with a poster filled with diagrams and a set of small plastic containers and a glass case. A video slowed to 0.1 times shows falling leaves.
So in one state, it's flat and it tumbles really far away from the original drop location, but we can control the transition without having a battery, all while it's in the air. And in this state, it's the stable state or transition state, and it actually falls like straight down.
A slowed video shows the robot drifting down in a tumbling state. A fan blows from the side causing the robot to fall far away from where it was dropped. Presses into the center to transform the shape. The corners point upward. Another slowed video shows the robot falling down in a controlled, straight descent. Stable state. A fan blows from the side but the robot falls straight down from where it was dropped.
And controlling the two states allows us to control how far away these devices float in the wind from the drop location.
A comparison video shows the stable state and tumbling state inside contained tubes with wind speed of 1.83 meters per second. In the stable state it floats near the top and in the tumbling state it bounces down the tube from side to side.
These things could be used for environmental monitoring, anything from climate change to even monitoring different insects.
He works on a computer. A video shows him operating on a microscopic circuit board. And he looks through the microscope.
I really like the idea of having our own personalized robot butler that's able to perform everyday household tasks for us.
Jia Fei sits at a desk and types on a laptop and a computer with multiple screens. As he codes, a 3D model of a robot arm plays on one of the monitors.
So in my research, I look into developing scalable and intuitive approach for collecting large-scale robot data that's able to train such a robot in our own home.
So the Allen School for NLP is like the holy grail. It has a lot of people doing great work and very diverse work too. Not only that, but also we get to collaborate quite often with other institutions.
Melanie types on her laptop which displays code.
So it's a big place to be doing AI.
I'm also the co-founder of Avella, a vision for engineering, literacy, and access.
His shirt reads, Avella, a vision for engineering, literacy, and access, in multicolored letters with illustrations of a rocket ship, gears, an atomic diagram, arithmetic symbols, and a cluster of hands making fists in the stars.
Avella targets underserved youth in the Seattle area, predominantly Black, Hispanic, and Latina youth. The Allen School has actually helped fund the Africatown Community Land Trust. They have the William Gross Community Center, which is like a local makerspace down near the Central District, where we've been going and teaching classes each quarter. Hopefully together we can help impact the next generation of K through 14 students.
He presents a scientific diagram to children on a projection screen in a classroom. Later does a craft project with the kids.
The reason I decided to join the robotics lab here at the Allen School is because I've heard many good things that come out from the research here. And not only that, we receive a huge amount of support from the faculty and from our industry partners.
Jia Fei holds up a tablet with the robot arm model and aims it at a kitchen counter. He reaches his own hand into the video field in front of the tablet's camera and moves it around.
My name is Melanie Sklar.
My name is Kyle Johnson.
My name is Jiafei Tuan, and I'm CSE.
I am CSE.
I am CSE.
Logo, Paul G. Allen School of Computer Science and Engineering. Text, cs.washington.edu